Welcome back to Data Architecture Day. We are starting session number 3 with Philipp Krenn. I'm going to switch over and we see Philipp's webcam. Hello.
Yes, I can see myself. Hi. Good morning, welcome, wherever you are. I'm based in Europe, so for me it's kind of the afternoon already. But I guess this is the advantage of these new times where everything is virtual, that regions don't really make much difference anymore. So hi from me. Let's see where we can take this, right? Anything else from you, Kevin, before we kick this off?
No, please take it away.
Okay, then let me share my screen and I guess we're good to go. Yeah, I'm monitoring the chat on the second screen. So if you have any questions, just let me know and I'll try to react to those. I will see. So let me get back to my questions. So topic is make your data fabulous. And the general idea here is mostly about trade-offs in data stores. So I will introduce you what is my background and what I'm using for my demos. But the general idea here is to really talk about the trade-offs that you have in data stores. So I work for Elastic, the company behind Elasticsearch, Kibana, Bytes, Logstash. We have various products there. My official title is developer advocate. So I mostly spend my time trying to educate people and show the good parts of what we do. And today is kind of no exception, though what I will tell you is pretty broadly applicable. If you have never seen our stack, this is what it looks like. And I'll only kind of focus on the top 2 parts here. So only Elasticsearch that stores the data, which I don't want to say it's like a database because we're very careful not to call ourselves database because we don't have transactions or multi-document transactions and things like that. That's why we always stick to that data store terminology. And then Kibana, which is the visualization on top. So it's kind of the window into your data. To get data to that stack, you could either use a REST API or Bytes, which is like a lightweight agent, and Logstash is more like an ETL tool. But we don't need those today. I have some data put into Elasticsearch already, and then we can query that and see how that develops over time. So, knowing my background, what is the perfect data store solution? And just for the interaction, I see the chat. You can just type plus or minus for a yes, no question. If you have any proper questions, just type a Q and I can wait for you to type out your questions. So I will try to not run off before we can cover your question. So what is the perfect data store solution? Any guesses? Yeah, I hope you can hear me correctly. A hybrid approach is the perfect solution. So probably a hybrid approach is the true answer. But what I want to kind of like push in this talk is what you often hear, it depends. And this is also often when you are a consultant, this is the favorite answer that you want to give, because then normally you start charging a lot of money to figure out what that it depends really depends on. And I think it depends is totally the right answer for a complex question. It's just like you always need to specify what it depends on. What are your trade-offs? And this is exactly the idea of this talk, that I want to go more into the trade-offs. And in chat, I see various ideas like something that is flexible and fast, the file system that is indexed, whatever fits the environment. All of those are the right answers. And I think it's really about having this, picking the right trade-offs for what you want to do. We're kind of past of these good old days where you said, okay, our database is X, and we always use X no matter what we try to solve, but you want to have some more flexibility around those trade-offs. So that is really the idea what I want to dive in. And that's why you need to pick the right trade-offs for your environment. And what is not really true, even though sometimes people try to tell you otherwise, is it's not all magic. There is not one system that is magically better than everything else. It's really just about picking the right trade-offs for your specific solution. So, talking about trade-offs, probably the best known trade-off in databases or any data sources or anything that keeps data is the FAB theorem. Not sure you have heard of it, but I want to go quickly through the FAB theorem and the trade-offs that it has in it. So FAB stands for consistency, availability, and partition tolerance. And it is based on this paper that describes those attributes. It's from sometimes in the early 2000s, if I remember correctly, or late 90s. And it is really about the trade-offs that you have in any system that has data in it. So the three attributes that you want to have, consistency, availability, and partition tolerance, let's go through them, what each of them means. So consistent or consistency is that you have a total order on all the operations that you run through. So the assumption is, even if you have a distributed system, that it looks like you have a single pipe where all the commands pass through. So it's really one after the other. So there is a total order of what came first and what came after in terms of commands, which is reasonable. So you know how a query should respond. So it could not be that sometimes you insert data first and then you run a query, and on other nodes you might query data and then insert afterwards, because that would give you potentially different results. So it looks like you have a total order on your requests. Next up, availability. Every request that is received by a non-failing node must result in a response. And the point here is basically a node cannot decide not to give an answer. So it cannot just say like, ooh, I'm not sure what the state of the cluster is right now, so I decide not to respond to it. So, but it must really give an answer, whatever it thinks is the right answer right now. And finally, partition tolerance. The network can lose arbitrary messages, or it can just break in the middle. And the thing about partition tolerance is that it's pretty much a given in any distributed system. So as soon as the network is involved, bad stuff can happen in between nodes or individual nodes that can fail. And it's very hard to tell what is the correct state right now. So partition tolerance is really having this flexibility around partial failures in your system, which leads us to this picture, which tries to show you what the trade-offs are in the FAB theorem. Or basically it says you have these three attributes, you want to have all three, but you can only pick two at most. So you can see there is no middle or center where you have all three attributes. So some systems pick consistency and availability, others availability and partition tolerance. And finally, there are some systems picking consistency and partition tolerance. But you cannot have all three. And just to give you an idea what that FAB theorem really means, let's assume you have a 3-node cluster, and then the network breaks in the middle. And then on one side, basically you have 2 nodes, and on the other side you have 1 node. And then your clients start putting more data into the 2 nodes on the one side. And then the node on the other side has to decide. So first off, we're in a partition tolerance or in a partition state, so that one node is partitioned from the other 2. And it has not received the write operations or the potential write operations to the other side. And then it has to decide, am I consistent or am I available? Because it can either give whatever data it has right now, and this is the answer that it provides if it gets queried, but then it might potentially miss out on the write operations that happened on the other 2 nodes. Then it is available because it's answering, but it might not be consistent with the rest of the data nodes. Or it can decide, well, I don't see the majority of the network, so I'm not sure what is the current state, so I don't want to give an incorrect answer, so I'm not answering. Then it would be consistent, but it wouldn't be available anymore because the node basically decided, I'm in a weird state, I'm not answering your queries. And that is really the idea of the FAB theorem, that when something bad happens, you have to decide, am I consistent or am I available? And if you don't pick those trade-offs explicitly, something random will happen, which is potentially worse than having picked explicitly what is the right answer to your problem. There are 2 common misconceptions or problems with this. Partition tolerance is not a choice in a distributed system. I know that especially initially, like 10, 15 years ago, people were saying, well, our network is so stable that we don't have those, which is probably not true. Either you have been exceptionally lucky or your monitoring is just not good enough, so you don't even see them. What you have oftentimes is you have lots of small failures somewhere. There was a very nice paper and description of, for example, on Azure, on Google Cloud, on AWS, how many nodes they lose each day, how many racks die per week, how often an availability zone goes down on average. And they have all these kinds of failures that play into that cap theorem. So you cannot just say like, we don't have those, because pretty much everybody has those problems. And then you just need to pick what is the right trade-off there. For the comment, I see with the latest algorithms and services, you get pretty close to having all three. Yes, there are these trade-offs where you try to get all three, but normally where you play is that you have very strong guarantees around your hardware. For example, Google has built some fancy technology where they had GPS-based clocks in their systems, just to make these windows of error very small. But in the event of something bad happening, they still have, for a very short amount of time until they manage to automatically fix it, you still have these basic trade-offs. Just because if you have that connection cut, for example, between 3 nodes, you need to decide what is the current state, even though you can maybe recover that in a second or less. But even during that second, you will have to decide, am I not responding to queries, or might I give outdated information for a very short amount of time? So you get very close, but you don't really get around it. Okay, second misconception. Consistency is unfortunately an overloaded term. So in ACID, the transactional attributes of relational databases, for example, consistency is a predicate. So the consistency there basically means you move from one consistent or correct state to the next. So you have a not null constraint, you have a reference, you have a data type. You basically, every operation moves you from one correct state to the next. That is the consistency in ACID. In the cap theorem, consistency is about the ordering or temporal. It's like at one point in time, do I have the same view of data over all the nodes? Or is at one point in time, could some nodes answer a query differently than some other nodes? So there it's the linear ordering. So in the cap theorem, you might have the wrong linear order, while you still have the consistency in the ACID sense, like you don't violate any rules around it. So those you might have. So how could you describe that to your kids? Since I guess most of you have kids at home now, you could tell them what you have learned today. And Robinson Crusoe is a very nice description of the cap theorem. Because Robinson Crusoe is sitting on his lone island. And I think he was British originally. So let's assume a ship comes by and asks him a current question. And the question might be, who is the King of England today? So Robinson Crusoe is partitioned from the rest of the world. And then he has to decide, am I consistent or am I available? And obviously, if he answers he's available, but his view of the world might not be consistent with everybody else, because his information might be outdated. Or he could decide like, oh, I'm not answering because I don't really know anymore. Then he is consistent, but then he's not available anymore. And that's really the basic idea of the cap theorem and how you could describe it with Robinson Crusoe. By the way, does anybody recognize the island? I'm just curious if anybody has been watching movies in the last, I don't know, around 5 years or so. Because this is where all the demo samples that I will run through will be coming from as well. So if you don't remember where this is from one of the recent Star Wars movies. This was where somebody was partitioned from the rest of the world. And this is where we will take our examples from. So all my examples will be based on Star Wars. So sometimes people say like, oh, you can break the cap theorem. And yes, you can, but that doesn't necessarily give you a very useful system. So for example, here, if you use def null, it does break the cap theorem because it will always give you the answer, like nothing. And it's always available, but this doesn't make it a very useful system. So breaking the CAP theorem is kind of possible, but maybe not in a very useful way. Okay, next up, something we call the FAB theory. And if you remember the title, Make Your Data Fabulous, this is where this wordplay was coming from. And FAB is not an official theorem or whatever. It's just a theory that we have built up internally. And again, the idea is you have 3 attributes and you can only have 2. And I will go through them just to discuss some more trade-offs. It was built up by one of my colleagues, Mark, showing him doing his favorite hobby, skateboarding. So let's see what Mark has come up with. So the 3 attributes that you want to have are fast, accurate, and big. So fast is pretty intuitive. It's something where you get an answer in near real time instead of something that is being batch processed. So my intuition is like anything that you wait for as a human to get the answer and you don't switch to another tab or window on your computer because it takes so long, that is good enough for that near real-time calculation. It's also nothing where you would go to get a coffee because you know this batch job will take so long. Some systems that often don't have that is like either batch processing, or the Hadoop world also has had this approach to some degree, that you run a job that might take more than 10 seconds, minutes, maybe even hours until it completes with the result. But what you generally want as a human, you want to have a fast enough response time that you just wait for it. So fast is one of these attributes that we want to have. Next up, accurate. Instead of approximations, we want to have exact results. So this is really the value that we have for something. And this one sounds pretty intuitive that everybody really wants to have that, but we'll get into the details of that one because that is one of the more interesting attributes in my opinion. And finally, big, it's any workload that you need to parallelize that you cannot handle on a single machine anymore. So anything that you cannot run on, I don't know, your laptop, for example, anymore, that might be in that big category. And that's the general idea. You have either so much data or you need to have so much processing and querying in parallel that you need to spread out the load and you need to have some horizontal scaling. So that is potentially an attribute that you might want to have as well. The one thing where I'm kind of careful is big data is not one of my favorite terms. Because it's horribly overloaded and abused by marketing. So I'm trying not to call it big data because, yeah, it might just give you the wrong idea of what we're talking about here. So it's not about the buzzwords, but really just about the trade-offs. So let's dive into the details. So I think fast and big are relatively intuitive to understand. Like fast, you wait for a result. Big, you need to scale it out. What might be a reasonable trade-off for accurate? Like, why would I ever want to get wrong results back? Like, nobody would want to get that, right? How could that ever be useful? And let me show you why this might be something that could be interesting to you. So my examples will use Elasticsearch, unsurprisingly, but it applies to many other systems as well. So some of the same trade-offs that I have here, you will have, for example, I know in PostgreSQL as well. So this applies widely to many systems. The only thing that you really need to know about Elasticsearch, and if you have any questions, just shout. The only thing that you really need to know is that the unit of scale is a shard. So basically you have an index, and it's not really a table, but you can kind of think of it as something like that. So it's some data that belongs together, but you can break it up into smaller pieces in so-called shards. And those shards you can distribute over multiple nodes. So this gives us the big attribute that we scale out some data or workload over more than one node. Sometimes people ask, like, where is the term shard coming from? Does anybody remember this picture? Because maybe there are multiple stories of where the term shard is coming from, but this is the story that I believe in, where shard actually originated. Does anybody know which game that was? And I must admit that I have never played it.
It looks like Baldur's Gate.
So this one is, I think, from Ultima Online.
Ah.
So I might be wrong since I've never played it. But the idea here is, or the story to it was that there was this evil wizard, and the world was trapped in some crystal. And then the crystal was shattered, and you had these shards or pieces of the data, and those were copies of the world or pieces of the world that you could play. At least according to this blog post here, which has already been around for quite a while, this is a story that I believe why shards are called shards. Maybe there's another story, but this is the one I believe in. Okay, so let's run through some queries based on our shards. So I'm using a terms aggregation. The terms aggregation is really just like which term is most common, which might be some calculation that you often run through. And I'm using okay, never believe Lord British in the comments. Might be true. But for example, for the sharding, it doesn't really matter where it comes from, but I think it's a really nice story. So here I have the word count of the original Star Wars movie. So counting in Star Wars is kind of weird. I think it's Star Wars 4 by now, but it was the very first that came out a long time ago. And according to somebody who did the work and counted, Luke was said 64 times in that movie, and R2 31 times, and Alderaan 20, Kenobi 19, etc. And I have created 64 documents. Think of that like a row in a relational database. 64 documents with Luke and 31 with R2. Etc. So I've created all these documents, and now I want to do that calculation. Which one is the most common term, and how many times does it appear? So what did I set up here? I created my index Star Wars with 5 shards, so it can be split up or is split up in 5 pieces that we could put over up to 5 nodes, or one physical node could also contain multiple copies. I'm using 2 nodes in the cloud, so it will be just spread out over 2 actual nodes, but we could spread this out over multiple nodes here. And I have created, like I said, 64 documents with Luke. And don't be confused, the first line here basically is the meta information. So I just say like the next line should go into that index called Star Wars. And we'll get into the routing information and some other pieces a bit later on. But this is just what I'm generating here. So I have the second, the fourth, etc. line. These are the small documents that I have created. So we have Word with the value Luke, and I have 64 of those, and 31 for R2. And then you could do something like this. Let me quickly show you live, like we can do this one live here. So you can just create the visualization. So this is a so-called tag cloud, and we can just build the tag cloud. I need to grab the index pattern here, which is called Star Wars. Then it's calculating or giving me that visualization. By now, it's just showing me the size here is the groups that I have built. So this is all the documents together. What I want to do is I want to break this up into individual so-called buckets and based on the terms. So this is exactly the terms aggregation that I have described before. I want to get the top 15 terms over all the documents that I have. And when I run that, and I need, of course, to pick the field on which I want to run this. When I run this, this is what you get out of this. So you can see Luke is the most common one, and R2 is probably the second most common one. The question here is, does it really matter how many times each one appears, or is an approximation good enough? And the idea here is that an approximation is probably good enough. You want to have a fast result, especially over a very large data set, without wasting too many resources. And you have, like, if you have a slight error in the results, that's probably good enough. You just want to get an approximate view what is most common here, and this works. The calculation in the background might be correct or not, and we'll actually jump into the details of this query here. So let me show you a bit what is happening behind the scenes. So if you have never worked with Elasticsearch, it has a REST API, so it's just HTTP calls and then JSON documents that we send around. And you will really start to appreciate SQL once you need to type all those curly braces. But this is what we do here. So this is in Kibana, it's called console. It's basically a place where you can just type your different queries. You have auto-completion and syntax highlighting, and you can just run through your queries. So this is very nice for a demo. So I have my current version of my Elasticsearch running here. And at first, I just want to get a quick overview of what data I even have. So I run a query. Any guesses what this query here would be in a relational database? And this should be a simple one. Probably something like select star from Star Wars where word like Luke or equals Luke. Something like that should do the trick here. Yes. So this is just running through all the documents and queries, how many looks do we have? And you can see a couple of pieces that are relevant here on the right-hand side in the result. So it will give us the top 10 documents back. And you can see further down, we have one loop here. But overall, it tells us that we have 64 loops that we have found. So this is the right number because we have inserted 64 loops. And it will then give us 10 of the high or most relevant documents for this one. So we have the right amount of information here. And now I want to run this aggregation. So here, that query is the aggregation that I was describing. Let me make that slightly bigger because I can see it's kind of hard to read in the stream. Okay, so what we have here is on the Star Wars index, we run an aggregation. I give it the name most common. And then I run this terms aggregation on that specific field. So word, keyword, I want to run this. There are two size attributes which might confuse you. The first size is I want to have the top one document. So I only want to know which is the most common document. And the size 0 at the end says, I don't want any of the actual documents back. I just want the aggregation, because otherwise I would get 10 documents which form that aggregation back. But I don't care for those. I just want the calculation. So when I run through that query, it gives me an error, or it gives me a result. And now suddenly it tells me that Luke appears 60 times in all my documents, which is not correct. And I know what you might be thinking. Let me switch over here. Probably you think, well, it's impossible. It's what Luke is trying to tell you here. Why are we calculating wrong here? And this is really the trade-off in that data set. So for that, we need to take a look at how I've prepared the data. And I've kind of cheated or skewed the data a bit so that it doesn't calculate the right thing. So I have basically distributed the loops unevenly between the shards. So some shards have only 1 or 2 loops, and other shards have like 40 loops or so. And that is exactly the trick that I'm using here, that for the first 10 documents, I'm using a different routing key. So the routing key will decide to which shard those documents go. And then for the 54 remaining loops, I always use the same routing key. So they always go to the same shard. So they will be unevenly distributed. I guess you don't need to see the script. I'm just having a very simple shell script, which is generating the documents and inserting those in that unevenly distributed fashion. The one thing that you need to know is, how do we route one document to a shard? And basically the shard number is decided by this calculation. So we take that routing key, we hash it. The hashing algorithm is called number3. And then we calculated modulo the number of primary shards. So we had 5 primary shards, so I calculated modulo 5. Why do I hash the routing key? Does anybody have any guesses why do I add this? It's kind of unnecessary work, right, for the distribution. The assumption is that my routing key might be, for example, you could just use names, and then some names might be similar to each other, and then you might have like a peak in some places of your entire routing information. So you might have E is the most common letter in English. So you might have more people in one specific place that get routed to one specific shard. So your shard would get an uneven amount of data. That's why you hash the routing key. And that would normally guarantee that your routing information or that your keys are evenly spread out over the entire key space, which I have explicitly circumvented by using that routing key to route everything to the same, or many documents to the same shard. So we have this uneven distribution of data. And I can actually show that if we run through this query here. This shows us, let me slide that over slightly so you can actually see it. Here you can see we have the Star Wars index and we have the shard, so 3, 2, 1, 4, whatever. And you can see the number of documents. You can see that shard 3 has by far the most documents. And then, for example, shard 1 only has 24 documents. And this is exactly because I skewed how the data is being distributed and why this then will be calculated wrong. You can also see I have 2 instances running here. So 43 and 42 are my instances. And the data is just spread out between them. So why are we calculating wrong here? Let's run this query to figure out why this is being calculated wrong. So what I'm adding here, that is the only difference to before, is I add this show term doc count error true, which is a very long name. But what it basically does is in the query, you see Luke with 60 documents, and right under it, you see doc count error upper bound 4. So it knows that there might be 4 documents missing, which is, by the way, exactly the count that we should have. So 64 would be the right number. So it tells us there might be something off here. Also, in total, it tells us how much off we could be in total over all the document with the doc count error upper bound. So it does warn us. And now the question is, why are we getting that wrong calculation? So for that, we need to discuss, like, how do we calculate how many results we're getting back? So what we're getting here is, if you want to have the top 1 term out of all the shards, you could get all the terms of all the shards and then combine them to get the perfect result back. But let's assume you have 1 million unique terms. Then you would need to get from every single shard, you would need to get that entire list of how many times does this term appear. And then you might need to combine 1 million sub-results from each shard onto one node to get to the total number, which is maybe a total overkill because you're only interested in the top 1 result. And this would require a lot of calculation in each node and then a lot of transfer on the network to that one so-called coordinating node to actually give you the actual result. So as a trick, what we are doing here is we are only returning for each shard, we're only returning something we call shard size. And that is basically size is the number of how many top n documents basically we want. So size is 1 in my example. You multiply that by 1.5 and then you add 10. And this is how many sub-results each shard sends. So these are the top n results from each shard. Which in our example, what does that come down to? So we have 1 times 1.5 plus 10. How many sub-results is each shard forwarding? And well, 11 or 12. Which one will it be? So this is being rounded down. So each shard is basically returning the top 11 results. And then the coordinating node is calculating out of those top 11 results for each shard, how many documents that is. Which leaves us with the question, okay, we have 11 documents per shard. We have 5 shards. So basically we get 5 times 11 sub-results to calculate, which is much better than, let's assume you had 1 million unique terms. This is a much smaller data set that you need to aggregate. And the assumption is if your data is evenly distributed, the top 1 result will be in the top 11 for every single shard, which is not true because I have kind of intentionally skewed my data. And only on some shards, it's in the top 11. And in some shards, Luke is not in the top 11 results. And that's where we are missing out on some loops. And this is what I have basically done here. And this is what this is also telling us, like how many documents we're missing out and how many other documents were not included in that calculation. So how can you fix this? So we have run through that query and seen those results. What you can do is, and this is the right query to run after that. So I got a question in the chat, why 11 and not 15? So the size was 1, you multiply it by 1.5, which is 1.5, and then you add 10. So you have 11.5, and that one is being rounded down. That's how many sub-results you send for each shard. I hope that answers it. It's the n, how many results you have, or want to have, times 1.5 plus 10. And I'm not logged in, so I cannot send you the message, but that's the right calculation. So this is what you would get back by default. What you can now do instead is with shard underscore size, you could overwrite that calculation and say, I want to have that many sub-results from each shard. So now I'm saying I want to have the top 20 sub-results from each shard. So we have 5 shards, 20 sub-results, so it would be 100 rather than 55 then. And then when I run this query, so let's see here, I have set that shard size to 20. So it's 20 sub-results for every single shard, and I think we only have 16 terms or so, so this must be correct. If I run this now, now you see we have 64 results, which is the correct one, and we also have an error bound of 0, because we know basically the Luke, which is the top 1 document, was in every single shard. There is no margin for error here. All the shards returned a value for Luke. We added those up, and the result is correct. But as before, we had to calculate like fewer top n results for each shard, and then had fewer to combine. And this is exactly the trade-off that we have picked here. So we wanted to have faster, less resource-intensive queries for a bit of a trade-off in exactness of the result. So this is what we have done here. And this was one of the trade-offs that you have. Okay, so this was the first example here. There are some others, or I want to go through 2 other examples to show you how those are going. So cardinality aggregation. How would you naively do a cardinality aggregation? So cardinality aggregation, I hope everybody is with me there. It's the number of unique terms. So how many unique terms do I have? And I think the right answer in my data set is 16, because I have Luke, R2, Alderan, and a couple of others. So 16 unique terms in total. The naive implementation would probably be something like a hash set. So you create a hash set, then you add each one of those. A hash set doesn't have duplicates. So one Luke would override the other Luke, and at the end you can just run size on it, and it should give you the number of unique terms. Why are you not doing that? Because this might be very expensive again. Let's assume you have 1 million unique terms again. Then you would have the hash set would contain 1 million entries. And that would just grow linearly with the number of unique terms in terms of both the add operation, but especially in terms of memory. You would need to keep 1 million unique terms in memory and do that calculation, which is probably an overkill if you run many of those queries. So you could do this differently. And let me take a step back and we talk about something else what you could do. The chance of a coin flip. What is the chance of having 3 heads in a row? What is the chance of that? 1 divided by what would be 3 heads in a row? So the chance for each coin flip is, let's say 1/2, because it always lands on one side and doesn't stay straight up. So it's always 1/2, and then basically 3 in a row you have 1 divided by 2 times 1 divided by 2 times 1 divided by 2. So these are the chances that you have. So for 3 coin flips, it's 2, which are the options, to the power of 3, the number of coin flips, which gives you 1 in 8 is the chance for 3 of those. Yes, 0.125, exactly. And you can generalize that if you have 2 options, it's 1 divided by 2 to the power of how many you have in a row. And you can use this to make a simple estimator function. So we assume we have an even distribution of data between 0 and 1. And how we do that is we hash our unique values, and then we store, and the hash value gives us 0 point some value. And then we just remember the lowest one of these. So the lowest one out of these values is 0.07. So you do the first calculation, you remember that value. The next one is higher, so we throw away that one. And we remember only one single value. Nice. You actually put in the formula and did the calculation for you in the Twitch chat. That's a nice feature. I didn't know about that either. So the estimation cardinality is 1 divided by whatever minimum value you have here. So out of all the hashes, 0.07 was the smallest one. So the estimation here is that you have 14 unique values in that data set. And you could generalize that in binary, that we count the leading zeros, which is pretty much like the coin flip. Like, what is the probability of having, and leading is counted from the end here. So what is the probability of having 3 leading zeros? It's again 1 in 8, or generally that formula that we have seen before, 1 divided by 2 to the power of k. And that is exactly what we do here, or what the naive approach would be. So you take the values, you hash them, you just remember the smallest one or the highest number of leading zeros. And from that, you assume, okay, approximately this is how many unique values you have. Now, this gives you a very rough estimate. So for example, here, that turquoise area, that shows you if you have a single estimator, so you hash the value once, and you remember the lowest value, how close are you to the actual value? And this is approximately the distribution, so it's pretty wide. And the clever part here is that somebody came up with an approach called LogLog, that you average that out and then calculate the average, and that gives you or less margin of error, which is this gray center, or the gray curve in the middle, which is the better calculation. Only how do you get efficiently to the probabilistic averaging over one value? So you could use multiple hash functions, but that if you use 3 hash functions, then your calculation would take 3 times longer, and you probably don't want to have that. And this is, by the way, the original paper for log-log counting of large cardinalities, which does describe this general problem. And the trick that LogLog is using is it's not using multiple hash functions, it's using a single hash function, but it buckets them. And what bucketing means basically is we calculate the hashes to some binary value for Luke, R2, and Jedi. And we use the first 4 bits we use for the bucket. And then we count the leading zeros from the end of the remainder. So 0, 1, 0, 0 is 4, and we have 3 leading zeros from the back. So this is the calculation, or this is for the bucket 4, we remember the value 3. Next up, for R2, we remember in bucket 9, we have 4 leading zeros. In bucket 0, we have 1 leading zero. And then you calculate like what would be the unique values for each bucket, and then you average the buckets out. And that gives you a pretty good approximation of how many unique values you have. And this is in pseudocode, the calculation for the log-log algorithm, which we'll just skip over now. Then Google improved that approach in a paper, and they called it HyperLogLog. In practice nowadays, it has been even further improved, and it's called HyperLogLog++, and that is the current implementation that Elasticsearch, but many other systems are using. That one is amazingly fast. So let's see what this means in the actual query. So what I do here is I calculate a precision threshold. This is basically up to this value, the calculation will be exact. For higher values, it will be an approximation. So I'm using a cardinality aggregation, and I'm trying to calculate the top, or up to 10, it will be correct, but we have 16 values. So if I run this, it will tell you there are 17 unique values. So it's close, but it's off by 1. Now you could tune that precision threshold, which basically more buckets, which will give you more precision. So it will use a bit more memory. But it will give you a more exact result. And even with a precision of 12, you already get the correct count of 16. So this is what we have done here. And just to give you an idea what you have, the precision threshold, I have made this artificially low to actually get this error, because by default it would be 3000. So up to 3000, your calculation would be correct. And for higher values, so 3000 unique values, for higher unique counts, it would be an approximation. You can set this up to 40,000. Any higher value would be capped at 40,000. So you cannot get higher precision on that one. And the trade-off that you have to pick here is in terms of memory. So for the precision threshold times 8 bytes, this is how much overhead plus the CPU to calculate all of those, how to get to those. And this is the error rate that you might get for the actual cardinality, like how many unique values you have, and what is the error rate in percent, how much might you be off. But even with 100, which is the red curve, you can see that the error rate is only like up to 5 or 6%. And if you have 10,000 as the threshold, you're around 1 or up to 1.5% off for the unique values at worst. So this is probably a sensible trade-off. I've shown you how these turn out. So one trade-off that you can still pick is, should you pre-compute those hashes? And you can do that either client-side, or there's a plugin you could calculate that. So should you calculate the hashes upfront to make the cardinality aggregation faster afterwards? What is the only right answer here? If you have paid attention in the beginning, it's always, it depends. And the it depends is if you have a large data set and a high cardinality on those fields, it is probably a good idea to do that. If you have a low cardinality, like a Boolean field, that doesn't pay off. Also, numerics are very fast to hash on modern CPUs. So it doesn't really pay off to calculate or pre-compute hashes for numeric fields because they are very fast to calculate. Yeah. There was a paper to improve that. It was called LogLog Beta, but we tried to implement that. We had a pull request, then we benchmarked the error rate and it didn't improve anything, so we never merged that. There might be another improvement, and those are called HyperLogLog sketches. So far, there's only a paper. We haven't implemented those. And it might give you more accuracy through some clever tricks in the algorithm. Okay. How much time do we have left? We have like 15 minutes left. Final example of how or where you might run into calculation problems. So inverse document frequency is how you calculate relevancy in Elasticsearch, or term frequency, inverse document frequency is how you calculate those. So let's look at one query that might be confusing. So here I have that full text search query that we have discussed earlier for loop. And when I run through that, one thing about, or that sets, or that is different in a full text search engine than in a relational database is that it's all about relevancy. And relevancy is this score field here. So basically this tells us how relevant is this document for the query that we have run. And the higher the relevant or the higher the score, the more relevant the document is. And by default, that is the sort order of how we return documents. Now, what is weird here is that this loop document has a score of 3.2. This loop here has a score of 3.1, even though it's exactly the same document. And as I scroll further down in my search results, you can see now the looks have suddenly only a relevancy of 0.7. Like, why is this look so much less relevant than the other looks? And that is one more thing where we run into this problem. So as in Star Wars, as they would say, let's see what we can do here. So in-term frequency, inverse document frequency. How that generally works is it has 3 parts. And by the way, the current implementation is called BM25, which stands for best match, and it is the 25th iteration of that algorithm, but we'll gloss over that. So what you have is, the assumption is if you search for Luke and one document contains the term Luke 3 times, it is more relevant than a document that contains Luke once, which if you try to graph it out would look something like this. So the x-axis is how many times do you have Luke in a document, and the y-axis would be the relevancy. And you can see if you have 3 or 5 Lukes, that makes a document more relevant than if you only have a single Luke. So that is the general idea here. Next up, you have the so-called inverse document frequency. And that is over all the documents, how common is one specific term? Or putting it another way, you try to dampen the relevance of very frequent terms, which looks something like this. So over all the documents, or over all the documents for one specific field, if you have Luke appearing only a couple of times, then it's very relevant. Whereas if Luke appears hundreds of times in that document, the relevancy keeps falling lower and lower and lower. This is what we're trying to show here. And the final piece is field length norm, which basically says shorter fields are more relevant than longer fields. So why is this relevant? So what you do is when you query in Elasticsearch, actually, you run a query and you run it against each shard, because we have broken out the data into 5 shards. I kept it simple here, and I only have how many? I only have 2 shards here. But what you do is you have a query phase where you basically, from the node 3, which is the coordinating node here, it goes out to the other nodes and queries every single shard once. So shard 1 and shard 0. And then gets back, these are the top n results for each shard. And then you have the so-called fetch phase where this coordinating node says, okay, overall, the top n documents are these 10 here. So 3 from this shard and 10 from the other shard, potentially. And then you only fetch the actual 10 best documents. So the first phase, let's assume your query wants 10 documents. In the first phase, each shard gives you its own best 10 documents, because they might be in the overall set of 10 best documents. In the second phase, the fetch, we fetch only the 10 actual best documents from all the shards, which leads us to the problem that the inverse document frequency is calculated per shard. So on some shards, we had very few looks. There the look would be more relevant than on shards that had many looks. You can fix that by actually fixing the statistics before the query. So it basically adds another hop before running this. So just to show you how this looks like, you can run this query here with this parameter, and then the calculation will be correct, because then the statistics will be kind of evened out over all the shards, and then all the loops have a relevancy of 1.5, for example. So these are all the same now because we fixed the shards. Should you use DFS query then fetch? What is the only correct answer for that one? It depends, but this one we are kind of more careful to say it depends. So yeah, first off, we have fixed that problem. It's good. What does it depend on? Performance. This is my favorite comic for any performance-related question. So every time somebody asks, like, will A behave better than B? It really depends on the scenario. Otherwise, you have this. This is especially common if vendors benchmark their tools and you have this benchmarking. They find a good scenario for their own tool and then a bad one for their competitors. But it really depends on the use case of what makes sense and what doesn't. Otherwise, you just have similar conditions, but yeah, the octopus will do better in the aquarium than the house cat to solve a puzzle. This is what you get in many benchmarks, so be careful with that. Our documentation, however, is pretty clear on don't use DFS query then fetch, because it really should not be required. Because normally your data should be evenly distributed amongst all the shards, so it should really not be necessary. It just adds more overhead, even though it's a bit hard to tell how much. Okay, we have changed the defaults of shards in the latest version because shards have a bit of an overhead and many people had too many. And also because you have seen all these problems we had was because we had many shards and then sub-results were coming from shards independently. So that's why we're kind of careful or why it might make sense to have a single shard. Now let's try something out very quickly. I've shown you this query before. You can see, let me slide it over so you can see that more easily. We have 5 shards and we have those on multiple nodes. Now what I do is I change this setting and basically I require all the shards to be, or one copy of a shard needs to be on this 43 node, and I block write operations. Let's see if that has succeeded. So yes, we have all the shards on one node, and now I can shrink the number of primary shards. So basically I take the index stars, I shrink it, and I put it into a new index called starlet wars, so the small Star Wars, because it only has a single primary shard. So when I run through this, this is acknowledged. When I look at starlet wars, you can see this now only has a single primary shard. So this only has one shard. So what does that mean for our queries? So if I run the full text search query, and I don't add that DFS query then fetch, I just run that query, will the scores be evened out or will they be off again? Any guesses? And I'll give you a moment to type plus or minus in the chat if you think that we still run into the same problem as before or not. Any takes on that one? So if I run that query here, you will actually not have this problem anymore because we only have a single shard. So the statistics are the same on the only shard that we have. So all the documents now have that 1.5 relevancy. Also, if I run the terms aggregation, will I still have the same problem that my calculation will be off? If I run that one, now my calculation is correct because you will get 64 documents back immediately. Because basically we're querying the top 11 documents for each shard. Since we only have one single shard, it will contain the overall top 1 document. How does that behave for the precision threshold for the cardinality aggregation? This one is not impacted because here it's more about protecting for memory, or the others as well. But here we still don't change the calculation. So this is still an approximation. So for the terms aggregation and full text search, a single shard will give you exact results back. A cardinality aggregation does not. However, what have we done now? So we have now basically in terms of the FAB theory, fast, accurate, big, we have now exchanged a bit of the big for the accurate. Because a single shard can only live on one single node, so we cannot scale it out anymore. So it is more accurate, but we have traded big for that. So it's really about the trade-off here. Oh yeah. So Simon, one of our co-founders, he always says, like, if you think about how many shards should you pick, use a single shard until it blows up, and then you can calculate how many shards you should actually use. I've shown you the other examples. And you might say that was kind of a cheap move because, well, we have traded big for accurate now. If that is the right trade-off, you will need to decide. There is no final answer to that. It's all about the trade-offs. That is really the point I'm trying to get across here. So you will need to pick the right trade-offs for your scenario. Sometimes you really want that scale and fast response times, and you're willing to sacrifice some accuracy for quicker queries or less resource use. In other trade-offs or in other scenarios, you don't want to have that. And this is really about the CAP theorem, but also the FAB theory. this is where you just need to pick the right trade-offs. Otherwise, you will run into the wrong use case or the wrong scenarios. Let me drop the link to the slides in the chat if you want to keep those afterwards. But I'm not logged. Let me quickly log in here, then I will. No, I don't have a Twitch account yet. I will. You can find it on my website. I will give you the slides afterwards. Let me stop sharing my screen, and we can do some questions here.
And if you want to drop the link into that chat,
I'm doing right now.
Perfect.
I should have logged into Twitch before. There you go. Any questions?
So we do have one question. Is it possible for Elastic to auto-calculate inefficient sharding and add or remove shards?
So right now, it's a manual process, but we have the so-called _shrink or _split APIs where you can change the number of primary shards, but be aware those need to be a factor. So 5 for the number of primary shards is not a good idea because it's a prime number. The only place where you can go in terms of a factor from a prime number is 1. So this is the only place how you could shrink that down. So if you pick something like 6, you could shrink down to 3, 2 or 1 primary shards. That might be better. Or you could go from 6 to 12, for example. There is a soft limit, I think 1,000 shards per Elasticsearch node, which is way too high. The general idea about shards is that you should have, it depends a bit on the use case, but it's like 10 to 50 gigs of data per shard. So you need to have multiple gigabytes of data per shard. That is the right approach. Otherwise, you don't need that many shards.
All right, wonderful. If there are any follow-up questions, what would be the best way to reach out to you?
Yes, so you can find me. Normally, Twitter might be the best place. I'll drop you my Twitter handle. This is where you can find me. I'll just use you as a proxy to forward those. Which Xera is my Twitter handle. That is, or you could also see Xera as the website where I post the slides. It's a rot13 of my last name. So if you rotate the letters by 13, this is what you get. So this is where you can generally find me on GitHub, Twitter, anywhere else. Only on Twitch, somebody took my handle before I could, which annoys me. But yeah, that's why I don't have a Twitch account, because I can't get the one that I want.
Perfectly reasonable.
Yeah, hacking. I know this is the only proper answer to that. Yeah, if you have any questions, just ping me on Twitter. Thanks for listening. If you have any questions, I'll stick around for a bit. Thanks for joining.
All right. So thank you very much for a great presentation. Now we are going to take a 20-minute intermission. Our next session starts at 12:40 p.m. Eastern Daylight Time. I'll, as I've done before, pop out for just a moment and then pop back in. So if you see the stream stop, don't panic. It'll be back very soon. So I'll see you on the other side.